one. Okay, so day one assignment and number 15. If I remember right, number 15, well, let me just project it up and then we'll get it exactly. Okay, an unknown gas diffuses 10.55 times as fast as phosphorus trichloride. What's the unknown gas? So things I'm given. Since it's talking about how fast, I know it has to be Graham's law because that's the only one that does with speed. And it's rate A divided by rate B equals the square root of the molecular mass of B divided by the molecular mass of A. Okay, so over here, what I've got given is I've got the rate A divided by rate B is 10.55. I also have that A, molecular mass A, is unknown. I know molecular mass B is equal to phosphorus trichloride. So I need to add up from the chart a phosphorus, which is 30.974 plus 3 chlorines at 35.453. I'm going to plug in what I've got to my work. So I get 10.55 is equal to the square root of, I'm just going to put PCl3, whatever you get for the mass there, divided by MMA, which I don't know. Then what I want to do is I want to take and I square both sides. By squaring both sides, I can get rid of the square root. So I'm just going to take this down. 10.55 squared is equal to PCl3's mass divided by MMA's mass. If I rearrange this, then I get MMA is equal to PCl's mass divided by 10.55 squared. And you'll end with your answer. That's 466. Okay? Any other questions that you'd like to go over? Yes?
D on day 2.
D on day 2. Okay? Day 2, question D. Put it over here so we can get a picture and move it up and get lots of room. So, a sample of argon has a volume of 0.43 milliliters. So, V1, 0.43 milliliters. At a temperature, T1 of 24 degrees Celsius. Right away, I add 273.15 and get the new temperature. At what temperature in degrees Celsius? I'm going to have to change it after I do the work. Okay, so ignore that until the very end. We'll have the volume of 0.57 milliliters. So I'm looking for T2. Whose law? What's cell constant? Charles. Okay, so Charles' law just basically says V1 divided by T1 equals V2 divided by T2. Now, one of you suggested, Brody suggested that we change it to liters. I don't have to do that unless it's the ideal gas law. All of them I do have to change temperature into Kelvin, but I don't have to change anything else as long as it's the same unit unless it's ideal. In the ideal gas law, it has to be in ideal units. Okay? So that the constant that we have will cancel out. So I like to rearrange first. If you want to plug in first, that's fine. So T2 is going to be equal to V2 divided by V1 times T1. Okay? And you just plug in. Now, I realized after I told you all the answers were down at the bottom, not all the answers are down at the bottom. Most of the answers are down at the bottom, okay, but not all. This is one of them. So once you get T2 here, you're going to subtract 273.15 to get it back into degrees Celsius. And this answer is not down at the bottom. Okay, any others? Yes. What do I what? Because it wants it back in Celsius, and I'm in Kelvin right here. Whoops, I'm in Kelvin right here. Okay. I have to do the equation in Kelvin because I can't have an undefined number for T. Okay. I. Okay, on day 2, I. Okay, what is a volume? So I'm looking for V. Occupied by 20.4 liters. Oh, this is V2. At pressure 2 of 1200 torr. I could call these V1 or T. I could do V1 here too. So I'm going to look for V1. STP tells me temperature and pressure, but all I really need is pressure because temperature is going to be held constant. So the pressure and torr is 760 at standard. So whose law? Oh, sorry, P1. That's P1. As long as you tie the two numbers that belong together, I could have called V2 and P2 P1, V1 and P1, and what I'm calling V1 and P1, I could have called V2 and P2, as long as they're tied together. What? 760 is from STP. When we were taking our notes last time, 1 atmosphere is equal to 760 torr, which is equal to 760 millimeters mercury, which is equal to 101.3 kilopascals. All these are standard pressure. Okay? It's Boyle's. Okay, and Boyle's is just P1 V1 equals P2 V2. Remember, temperature always has to be on the bottom. So we're looking for V1, so I rearrange. V1 equals P2 V2 divided by P1. Plug in. Okay?
What's the torr?
Torr is pressure. Okay, any others? Yes. Number 6 on assignment 1. Okay, so again, as you're looking through, make sure you grab your given. So it has a volume, V1. Is that number 5? Oh, the lower one, sorry. We'll move this up. Number 6. Okay, a gas has a temperature, T1, 19.44 degrees Celsius. Add to 73.15, get that answer. Okay, so I've used that. It has a volume of V1 equals 54.5 liters with moles. N equals 204.6 moles. What's the pressure? Well, the only one that I know that keeps N in is what law? Pervert. So that's the ideal gas law. Ideally, you're not a pervert. PV equals nRT, pervert. So I also know R is 0.0821 atmospheres times liters divided by mole times Kelvin. Since I'm trying to find pressure, all I have to do is take P equals nRT divided by V. Plug in, and you got it.
What do you do with the atmosphere times liters?
They will cancel out. These will cancel out all except for atmosphere. It's just units that tells you which ones it's supposed to be in. So the atmospheres will be the only one that's left because liters will cancel with liters, moles will cancel with moles, and Kelvin will cancel with Kelvin. It's up to you. Yes. What? H on day 2.
Some of these are worded weird.
Okay, what is the starting temperature of 150 milliliters, V1? When cooled from a temperature of, uncooled to a temperature, so this is T2. T1 we don't know. T2 is 33 degrees Celsius plus 273.15. And to a volume of 120 milliliters. So whose law? Charles, good. What is Charles' law? Good. So pressure dropped out, right, of the combined gas law. So we are looking for T1. I've got to rearrange it. So I should end up with T1 equals. Now, if you're not good at rearranging, just put the numbers in where they are and solve for what you don't have. That's okay. I like to rearrange it first. It's up to you. V1 times T2 divided by V2. Plug in. Yes. Number 14 on day 1. Okay, so this one, this is another Graham's law. I can tell right away because it says speed. Okay, so I put grams, and grams is rate A divided by rate B equals square root molecular mass of B divided by molecular mass of A. Calculators are back by the flag. Okay, so coming along, the first thing I come to becomes my A. So this is A. So MMA is the mass of sulfur dioxide. So I need to add that up from the chart. The average speed, that's my rate A, is 45.0 meters per second. My second one, B, here is nitrogen monoxide. So MMB is adding up nitrogen and 1 oxygen. I'm trying to find rate B. Okay? So as I go to put it in, I'm going to say rate B. And again, you can plug in the numbers first. I'm just one that likes to rearrange it first. Doesn't matter. Either way will work. Okay, so rate B is going to equal rate A divided by the molecular mass of B divided by the molecular mass of A. And you just plug in. Okay, did I lose somebody? Again, if you don't like to rearrange it first, just plug it in where it sits and solve for what you don't have. Tiankum. 8 on day 1. Okay, 8 on day 1 is just a plain stoichiometry problem. We're using our mole map on this one. And the hint on that is it gave me an equation. Okay, so we're just going to use our mole map going down to STP and back up, or back up and down. So it says how many liters of water can be made from that many liters of oxygen. So my given is STP, standard temperature and pressure, which tells me I can use the mole map. And I've got a volume of O2 equal to 35.765 liters. That's what I've got. So I'm going to start with what I'm given, 35.765 liters. And this one I believe I actually had on the board for you last time, O2. So then on the bottom, we're going to use the conversion on the mole map to go from volume up to moles. I want to get rid of volume, so 22.4 liters of O2 is 1 mole of O2. At this point, liters of O2 go out. Okay, and then the next step I do is using the equation, the coefficients in front. So for every 1 mole of O2, I get 2 moles of H2O. At this point, moles of O2 go out. Then the last step is now that wants to get me back into liters, so I say, okay, in 1 mole of H2O, there's 22.4 liters of H2O. And on this step right here, I can not only cancel out moles of H2O, but the 22.4 liters because I went from liters to liters. So basically, I'm timesing it by 2 and I got my answer. And that would be liters of H2O. Okay? How are we doing? Okay, 5 toddler rules. Go bug you again. Straight. Squirrel. So what does squirrel mean? Straight, random, line motion. Okay. What else? Not attracted or repelled. No volume. Not elastic collisions. There we go. And one more.
When it's higher temperature.
Higher temperature, higher kinetic energy, lower temperature, lower kinetic energy. In other words, when it's hot outside, I want to go play outside. When it's cold outside, I want my blanket snuggie and the Disney movie over and over and over again. Okay? Get real. So that was ideal, gases. Get real, teenagers. Attract and repel, have my own volume. Collisions are not elastic, right? Okay, I want my real gases to become more ideal. Low pressure, high temperature, non-polar situations. I can choose my friends. Okay, that's summertime. Great. All right, so we're going to go through the laws really quickly as a reminder. Pressure held constant. Charles' law. So V1 divided by T1 equals V2 divided by T2. Temperature held constant. Whose law? Boyle's. And what do I do with that? Times it across. P1 V1 equals P2 V2. Okay? Volume. Gay-Lussac. Volume held constant. How do I do that? P1 divided by T1 equals P2 divided by T2. So if they're right next to each other, temperature's always on the bottom. Okay? The only one that you times across is where temperature's gone. Okay? So we got, if all of them are together, it's the combined gas law, right? So we go P1 divided by T1 times by V1, or P1 times V1 divided by T1 equals P2 times V2 divided by T2. Okay, ideally you're not a perv nerd, which is PV equals nRT. Two other laws, two other gas laws. What are they? No? Grandma's and Dalton's. What's Graham's? It's the rate one. It's the one, rate A divided by rate B equals the square root of molecular mass of B over A. So they switch places. The what? The del one is Dalton's. Dalton's del law, which is all the parts equal to the one. Now, everybody gets confused on that because what? I've got one that I had to read off the table. That's when we do in lab. So if I'm bubbling a gas and I know the pressure total, but I don't know the pressure of the gas, but I know the temperature of the water, I can look on a chart and find the pressure of the water. Pressure of the water plus the pressure of the gas equal pressure total, right? So I take the pressure total minus my water, and I've got the pressure of the gas. Okay, so we are going to go on right now. We're going to take that quiz in a minute. I'm going to give you your notes first, and then I'll give you the quiz. After the quiz, what you can do is you can work on daily work 3. Oh, excuse me, we need to correct first. Let's correct first. Yes, we do. How about we correct right after my notes? Is that all right? Okay. So we'll do notes first. So if you didn't get finished by the time we correct, what happens is I'll have you get the ones that you have got corrected, and then I'll have them just circle with a green pencil that you should have picked up at the back, the ones that you didn't. And if you get to the point where I got assignment 1 done, but I didn't get assignment 2 done, I'm just going to have them draw a line where you finished doing it all the way across your paper so I know what you did get done, and I'll go back and correct the ones that weren't done at that time. Okay? All right, so because I really want you guys to stay up with us and keep going. So let me grab this and bring it across. Oh, wrong one. Okay, so grab your notes out. We are going to go through nuclear chem. Come on. So most people, when they think of nuclear chemistry, think of bomb, right? And if it's not a bomb, then they usually think of this, which is nuclear power plants or power plants. They usually don't think about medicine or food or fire detectors, but they're all used in those. We irradiate food so it'll make it from California to New York without going bad. Okay? We irradiate cancer to get rid of it. We also give you radiation to find out if you got a broken bone, right? X-ray. We also use it in fire detectors because a small amount will stop the radioactivity from going from the source to its sensor. So really quickly it can say if there's particles in the air, and that's how the fire detector works. Okay, so we're going to talk about who started nuclear chemistry, if this board will go forward. There we go. No. This is Madame Curie, whatever you want, Curie. She actually found a small piece of radioactive rock that she called a magic rock. Now you should have your notes out and be taking notes at this time. Okay. She carried this rock around in her pocket for a long time. She put it out on a photographic paper in the dark and saw that it had these things that came out of it, and she called it her miracle rock. Well, the miracle was that she survived as long as she did because it caused her cancer, and that's what killed her. Okay, so small doses of radiation are good. Large doses, not so much. Okay, she discovered radiation. Now, the types of radiation are alpha. Alpha is seen by 4,2 helium, and it basically, the symbol is just like a fish. Okay, it doesn't have this thing at the top. I couldn't find one that didn't have the thing at the top at the time when I made this PowerPoint. Beta is considered an electron. An electron is a beta, and the symbol is basically that. And that nuclear symbol is how we write it. Gamma is a very high energy pure ray rather than a particle because it doesn't have any mass. If you'll remember, the top number here is a mass number. The bottom number is the atomic number. What is a mass number? How much it weighs, but what does it include? Protons plus neutrons. Good. So mass number is protons plus neutrons. What's an atomic number? Just the protons. The bottom number is the atomic number, and it is the identity. It is which element I am. Okay? Actual representation is this one. This is the symbol. We'll get to the penetrating in just a minute. Yeah, we did it at the beginning of the year too, but we're redoing it because it's so much on the sage. The actual representation here, symbols here. Okay? We okay to move on? Anybody not okay? You don't have to. We'll be using them enough. Okay, here's some others. A neutron, this is its actual. Sometimes it's just an N. A positron, and a proton. So they can be written these ways. How many are Trekkies in here? Anybody? Trekkies, Star Trek? You know data? Yeah. Okay. Most things that we have run on electrons. He had a positronic brain. He ran on positrons, positive electrons. Ooh. Okay, so we can write any element on the periodic table, any isotope in a nuclear symbol. The mass number on top, bottom number is the protons, and we can also show the charge if it has a charge. We okay to move on? Okay, so now we're talking about penetrating ability. I can stop an alpha particle by just putting up a piece of paper. I can stop a beta particle by putting a 0.5 centimeters of lead. This is when you go to the dentist and they put that apron on you, that's what they're stopping, is the beta particles. It would take 20 of those aprons to stop a gamma particle, or 5 feet of concrete. And you need to know both. So penetrating ability, alpha can't go through paper. Paper stops it. Beta, 0.5 centimeters of lead stops it. Gamma, it takes 10 centimeters of lead or 5 feet of concrete to stop it. So when they make the nuclear power plants, they put what's called a sarcophagus around it, which is a big cement dome. And in that dome, they put some lead in the cement so that they don't have to have 5 feet all the way around it. But most nuclear power plants do have that 5 feet all the way around it. And at the base, usually have about 10 feet. So it goes up to 5 and back down to 10. Yes?
What kind of thing does an X-ray use?
An X-ray uses a little bit of both, gamma and beta.
What does it cause?
What does it cause?
Yeah, because I always get X-rays and they don't use the thing. So it's like.
Yeah, they don't use it. They don't use lead on you if they want to see that area, but they should be covering up like your ovaries or that so that they don't damage those. Yeah, well, they should, unless they're looking at someplace right there. Okay, let's go on a little bit. I already sort of talked to you about this. As far as mass numbers on top, atomic numbers on bottom, it's easier to not look at this and just go on to an actual equation. So, and I've already written on this one, so it's okay. So as I look at this, this is an alpha emission. So I would put an alpha emission. Emission goes on the product side. Decay would go on this side. If I said bombard or my brain just left for the other one. I'll think about bombard or capture. It goes on the reactant side. So this one is a decay or an emission. You'll notice all the green numbers. The arrow acts as an equal sign. So on the left-hand side, the top numbers are equal to adding up the top numbers on the right-hand side. And on the bottom, the same thing happens. The bottom numbers are equal to the bottom numbers on the other side. That's how we do nuclear equations. Okay? Very easy. Now, they can write this side over here like this, radium-226, or they could write it this way. When they do it like this, you have to look at the chart and be able to pull off what atomic number it is. Okay? Okay, so when we have a nuclear reaction and a beta emission, same thing happens. So beta emission or decay, we would write uranium-239, we get a beta, and we get neptunium. Again, the top numbers have to add to equal each other. The arrow acts as an equal sign. Okay? Bottom number, same thing. Everybody okay with that? It's pretty easy. Okay, so you should have some practice ones that you should be able to do really quickly right now. Okay? So your practice ones down at the bottom, we had, this one is not on there. It is on the back. Okay, it's on the back. So if you're staying with me, number 8 is what is up here on the board right now. Number 9, sorry, number 9 is in your notes. So if you're not staying up with us, you need to make sure you... Okay, so I've written the equations as we hit them on there, so you can write them down and have some examples. Okay, so the top numbers have to equal the top numbers over here. The bottom numbers have to equal the bottom numbers added together over here.
Why are these all RA?
Just because.
Should it be because it's like,
RA can decay different ways.
I mean, it has a different.
Oh, numbers? I probably forgot to go back and change them, that's why.
Oh,
So that should have been uranium. That should have been 4 is beryllium. So 3 and 4 I screwed up on, sorry guys. So 3 should, instead of saying RA, should be U. 3 should be a U instead of an RA, and number 4 should be a BE. So that's probably why you're having problems following me, sorry. So number 3 should be a U instead of the RA, and number 4 should be a BE instead. Okay? So they'll tell you how it will decay. Number 2 should be PO. Okay? So number 2 I screwed up on 2. PO. Okay, so other types of reactions, we can have 207 PO, and this is an emission or decay, where we get a positron instead of a beta. So we get a positron off, and we're able to add the tops together and figure out we end up with bismuth, okay, and the bottoms. So the bottom is 84. What number plus 1 equals 84? 83. So then we would look and find it was bismuth, and the top, 207 plus 0 is 207. So what happens in the decay process and the emission and capture and bombard is they're trying to get a more stable atom. Okay? Some others that we can do is electron capture. That's a beta on the reactant side. So if it's capture or bombard, it's going to be on the reactant side. If it's decay or emission, it's going to be on the product side. Okay, so that's where you're going to put it. Okay, going on. So here's our first learning check. See if you've got that on yours somewhere. So boron plus helium yields, okay, so this is number 5. Something plus a neutron. Okay, see if you can do it by yourself. Remember, the tops have to add together and the bottoms have to add together. And then we're going to do a check. It's a bottom, number 5. First page, number 5, bottom. The bottom number tells you what letter from the periodic table.
Wait, the bottom number tells you the periodic table?
Mm-hmm.
I was right.
Okay.
So what about the top?
How'd you do? Because 10 and 4 is 14 equals 13 plus 1 is 14. 5 plus 2 is 7. What plus 0 is 7? 7. What number is 7? It's nitrogen. And we're done. Okay? So the next one we're going to try is a little bit different. It just gives it to you in words. Okay, so let's see what we can do with this one. So on this one, it says write the nuclear equation for the beta emitter. So beta is going to be on the product side of cobalt-60. So cobalt, if we look on the chart, over here it's in the D, about in the middle by nickel, it's number 27. So I would write the cobalt with the 60 on top and the 27 on the bottom. And then I'm emitting, so I'm going right to my arrow. And what was beta? 0, -1 is a beta, plus what else? Finish the equation. The B or E, you can put E. So this is an older program, so I didn't have it quite right on top of each other. Because 28 minus 1 is 27, right? And this is 27. So 60 is equal to 0 plus 60. Yes?
What's that like on number 1, how it's like a super big number? How it's like 26 over 88 RA.
Okay, so then you have to subtract those two and find out what else you need to bounce the side off. Okay, so what do you need on the top? You had,
So you got 4.
so you need how many more to make them equal on both sides? Yep. It doesn't matter. That's not the number on the chart. The bottom number is. Bottom number's on the chart. Okay, so we have made a whole bunch of different artificial elements. Basically, anything past 92 is artificial. We've made it. So 92 is uranium. So anything past uranium, we've made. And we've made it by throwing neutrons at it, throwing other particles at it. How many have heard of the Hadron Collider? Okay, we'll talk about that more next time. But basically, they just accelerate particles up, and then all of a sudden they give them high enough speed, and they smash them together. Okay? Okay? We use radioisotopes all the time in medicine. That's especially important, guys. That's especially important when you go and get, when they're testing your thyroid to see how your thyroid's working or to see how your kidneys are working. They have to have a radioisotope because your kidneys and thyroid are not radioactive. They won't show up and they're not solid mass. They won't show up on an X-ray. So they have to put a radioisotope that they can follow with the X-ray. And it has to be of a certain strength. But they don't want to be too strong to stay in your body. That's why you drink that stuff. So they can trace where everything goes. And certain parts of the body uptake certain things. So if they want to study the thyroid, they give you, I believe it's potassium, because potassium goes to the thyroid. So they give you specific isotopes. But they want them to have a very short half-life, and we'll talk more about half-life next time, because they don't want them hanging around your body too long and being radioactive. Now, if you've ever had a radioactive test, they'll tell you, please don't be around young children for the next 24 hours because you're radioactive. Okay? All right, so here's an example of a gamma radiation. Yes?
How do you get rid of, like, radioactivity?
That's what we'll learn about next time. So, yay! You won't be here next time? Oh, no. Make sure you listen to the lecture then. Okay, so this one right here, when it is bombarded by a neutron, we actually get high energy ray off, a gamma ray. Okay? So as we're looking at this, elements beyond 92, they're made by adding a neutron. And what happens here is we have what's called a parent isotope. And it always gives daughters. Sorry, no sons. Always give daughters. And they take the daughters, and then the daughters decompose. Now, you notice I've written beta above the arrow. Sometimes they won't tell you that's happening. They'll just put a beta or an alpha above the arrow. And then you have to finish the equation. It's basically telling you a beta decay. So it becomes uranium-239. It decomposes, becomes Neptune-239. Neptune-239 becomes polonium. Polonium, Neptune, and uranium-239 are daughters of the parent uranium-238. This is known as a decay series. And the problem with leftover uranium is it goes through a series that takes several years to decay all the way. Okay? Wait. Okay.
Is it, like, wasn't there, like, in another country, like, there was a meltdown?
Yep, Chernobyl,
And they're just, like,
Russia. It's been 30 years since Chernobyl, and what happened in Chernobyl is they did a safety test, but the problem was they cut down all the safety precautions. They cut every safety system there was. They cut off the water. That was a cooling system. They took out the control rods that absorbed the neutrons that stopped the fission or fusion reaction. They stopped. Everything they did was, it was like, how stupid are you? Why do you think these are put into place? And what happened is, because, and we'll see it here in a couple of slides, the reaction happens so quickly and it starts with one neutron, and that makes it, let's see if we can get to it. Here it is. It starts with one neutron, and that one neutron makes this unsteady, and so it splits apart, giving 3 more neutrons that then hit 3 more things that then split apart and make 3 more things. It keeps, and it just blossoms really fast. So what happened is when they cut all these systems down and they let the fuel rods go, it became so hot so fast and they weren't ready for it that it actually melted their systems and they couldn't restart the cooling system. They couldn't put the control rods down in. And by the time the control rods actually fell in, there wasn't enough to absorb the neutrons. It was out of control. And so what they had to do is they had to have some people fly over in a plane at basically a suicide mission to drop a whole bunch of neutron acceptors onto the plant that had now basically lost its sarcophagus and everything because it was so hot to stop the reaction from happening. And by the time they put they're called neutron acceptors, or what they use in the control rods. They actually accept the neutrons and hold on to them. So instead of letting 3, 2 of them would be kept. Okay, so it would accept those 2. They flew over and dumped it, but by the time they got back to the airport, they had radiation sickness so badly they died within a couple weeks. So it was a sacrifice mission. And even now, 30 years later, there is a zone around Chernobyl that is a no person zone. Yeah, there is. There's several up on YouTube, and you can tell the ones that are done by Greenpeace because they don't want any nuclear reaction. But it was just stupidity. Now, we had one here at 3 Mile Island, and I'll talk about that in just a minute. So nuclear fission is what happens in nuclear power plants. I think I said fusion earlier, but it's fission. And fission basically happens in 3 steps. You have to initiate it. You have to get a molecule so it's unsteady and wants to decay. Okay? Once it decays, you need to have a propagation. Propagation is how it keeps going. You saw how one of them, once it made it unsteady, it actually gave off 3, and that's called propagation. And then you have to have a chain reaction. So those 3 then hit 3 more, and it keeps it going. So these are the 3 steps of the fission process. We have to control the chain reaction. We have to be able to say, okay, I'm going to absorb this many neutrons. So that's why we have fuel rods we can put down into the thing and control rods we can put down in the thing, and we can adjust how much energy is being given off. We okay to move on? Nope. So initiation, propagation, and chain reaction. I think I give you a picture of a nuclear power plant. That should be coming up pretty quickly. We okay to go on now? Okay. Before we do that, we're going to talk about the band of stability, and I'm just going to blow through that to this one, which is a bigger one. The band of stability, the black ones here are stable. The red isotopes are not. And so you can see there's a band there. Basically, up to 20, it's a 1-to-1 ratio. So for every 1 proton, I need 1 neutron in order to be stable. Once I get past 20, it gets to 1 to 1.25. And then a little bit farther, about 40, it gets to 1 to 1.4 or 1.5. So we get to this ratio where it's stable and where it's radioactive, where it's not stable. So this is what a fission process looks like. This is only with 2 neutrons being given off. Can you imagine what would happen if 3 neutrons were given off? How fast this would grow and expand, okay? We have about 103 nuclear power plants in the U.S. and about 435 worldwide. France gets 75% of its energy from nuclear power plants. The United States only 20. Okay, there are a bunch. Okay, now I drew this picture over here because most of you relate nuclear power plants to something that looks like this with steam coming off the top. Okay, that's actually what's known as a cooling tower. That's how they cool the water down. So let's talk about the 3 systems. The first system here in yellow is known as the generator or the reactor core. Okay, that system is closed, and it's a system that generates the heat. So if you were doing a coal power plant, this is where the coal would be heating the water to generate steam. Okay, this is a reaction that just generates heat. So then we run it through another closed system. Notice that the only time it comes even in contact, it's still inside the pipes. Okay, so the pipes heat up, the pipes generate the steam. And it just keeps going back and around. Then the steam is generated, and the steam turns a turbine. The turbine is where we get our electricity. In hydroelectric plants, we use water to turn the turbine to create electricity instead of steam. Well, once the steam is used, it comes down here. We need to recondense it so we can put it back through the system. This is a point where they used to use a river or a lake. The problem was they would bring it in at 27 degrees and it would come out at 38 degrees Celsius. A little too warm. Took my trout stream and made it a bass stream. I like my trout. Okay, so people around got a little upset. So then they started building these cooling towers. So instead, they have a set amount of water, and they route it into here and let it go around and around and around and around and around and around and bring it back out. So it cools down, and then they can reheat it. Okay? So this is a general. Now, they've changed a lot of things. This is an old version. They've changed a lot of things in the new power plants. Instead of using fuel rods and control rods, they now use pellets and control pellets. Right here. This is a nuclear core. The yellow part is the nuclear core. This black thing right here is a containment shell. That's 5 feet of concrete all the way around, at least, minimum. So if something goes wrong, usually it's with the pipes. We get a hole in the pipe. They shut the whole thing down. At 3 Mile Island, what happened is, and they have detection systems in here to detect radioactive leak, right? So something leaked in here, they shut the system down, and just a little bit got into this system. So they had to go scrub the system. Okay, what was released was about the amount of energy of an X-ray. But everybody freaked out. It's an incident. It's an incident. Okay, yeah. Compared to Chernobyl, not much, right? Okay, now last couple years ago we got one in Japan. What happened with that? Well, they had an earthquake, right? And then a tsunami, and then they had, I mean, it just, and the power plant was right on the edge of the ocean. They were pulling the water from the ocean and putting it back in hot. So there was a lot of things that, hindsight being 2020, you know, you go, why did you do this? Why did you do this? Why did you do this? You know, yeah, they're going to have some problems. So those that are doing nuclear, if there's anybody in here doing nuclear, you can talk about those. Yes. That's what nuclear power plants are used for, to make electricity. Okay, you don't have the problem of, with coal power plants, you don't have the problem of as much carbon monoxide, carbon dioxide, sulfur dioxide getting in the air, nitrogen oxides, because you're burning with those plants. So you're not causing air pollution. Now you do cause nuclear waste, but the waste from the nuclear plant is much, much less than that of a coal plant, because a nuclear power plant, you could fit easily in a football field for the whole year. About a yard deep. What? That's the problem. Right now, they used to store it in Nevada, and they had a site ready to go in Nevada, but then Nevada said no, and so now they're just storing it at the nuclear power plants in what they call cooling ponds, where they just put it underwater and just let it cool and not become as radioactive. There are scientists right now working on refining that used uranium to try and make it reusable again and take it and make it hot again. Okay, so they could. Okay, fusion. Fusion is where I take two small, okay, we gotta keep going here really quick. Fusion is where I take two small things and smash them together. With fusion, I get lots and lots of energy. That's what's happening on the sun, is fusion. Okay? It would be great if we could control fusion. A few years ago, U of U thought that they had controlled fusion. They said, yes, we have been successful at cold fusion. A whole bunch of scientists came in, they were like, ooh, ah, ooh, ah. Nobody could replicate what they did. And so what they said, it was fraud. The scientists had put down in their lab notebook something that was not true. And so then that scientist got blackballed and now is no longer, kind of thing. So you got to have, when you do research, you need to be able to replicate your data. Okay, so problem with nuclear fusion is the heat can't be contained. It gives me a lot of energy, like the H-bomb, like the nuclear bomb on Hiroshima. But it's really hard to control. Okay, I couldn't say, I want to drop the hydrogen bomb or the H-bomb right here and just have it damage 1 acre of land. No, it doesn't work that way. It just goes. Okay, so hot fusion is hard to contain. We're going to start here next time with half-life. So what I want to do is I want to pass out your little quiz. Do your best on it. When you get done, give it to me. It is an open note quiz, but not open neighbor. So I want it to be quiet while you're doing it. So you can have anything out that you have. Yes?
So, like, they drop nuclear bombs, so pretty much, like, people just get, like, melted.
Yep. Oh, we need to correct, too. So we're going to do that real quick.